Hi everybody, welcome to another video in Discrete Math section 8.1 application of recurrent relation. So we talk about recurrence relation already. Now just focus on the application part. And so a recurrent relation is a sequence of the equation that is spread in terms of the previous term. It could be more than one term. And the solution, if it satisfies the recurrent relation, and because we have the initial condition, is where we start and how to get from these steps to the next. So that is recursion relation. Now, I will focus on the application this problem in this section by going over a few interesting problems. So first one is the Fibonacci numbers. So this is the original problem proposed by Fibonacci in the 13th century. This is rather old. So the story is this. Suppose that we have a pair of rabbits, young rabbit. It takes 2 months for it to mature, and when it matures to 2 months old, it will give birth. Right? So now let's say we have a pair of young rabbit mature to 2 months old, and in that case, after 2 months old, it will give birth to this young pair of rabbit, and that will stay alive throughout. And after 2 months old, that young rabbit will become old, 2 months old. And then it will give birth. And of course, that pair of rabbit original will give birth again, so we have this pair. And we'll just keep doing that. So this process is repeating, and we just count originally 1 month, there's nothing, but after month 3, okay, actually after the second month they have to give birth, and then after that, after 3 months, we have one pair here and one young one, and after that give birth again. Just keep doing that. Yeah. So with that, we can summarize this as 1 1 1 1 2 3 5 8 and so on. So pretty much every number we add this to previous number give us the next, and just keep doing that. So this is Fibonacci sequence. Yeah, and this is how we write the solution. So Fn is the number of pair of rabbit after n months. F1 is 1, F2 is 1, right? That makes sense. How to find number of pairs of rabbit on the island? We add the number of on the island after the previous n minus 1 month and the number of newborn pairs, which equal to f of n minus 2. And so we just add them up, and that's what we have. So after that, the Fibonacci sequence, we satisfy this equation. This term is equal to the previous 2 terms add together. Of course, we talked about this in the recurrence relation earlier too. We're not talking much about this. So we'll focus on a little more on the classic problem of the type Hanoi. Right. Let me switch the camera. We make one adjustment. Right. Zoom out a little. Right. So I actually have that game here. Right. So the type Hanoi. By the way, I'm from Vietnam, and Hanoi is the capital of Vietnam. Right, so the game is this. You have 3 packs and the tower, which a bunch of this of different size. The smaller one on the top, the bigger one at the bottom. Right, so the objective is we move all of the discs here to here. And the rule is whenever we move, the bigger disc cannot stay above the smaller disc. Right, so how do we do that? Right, now let's take a look. The simplest case, if we have one disc, that could be it, one move. If we have 2 discs, we want this 2 discs to go to that 3rd pack right there. But we have to keep the smaller one on the top and the bigger one at the bottom. So if we move this directly like this, it's not going to help, because in that case we have to move this, and we didn't accomplish that. So if it's even like this, what we will start is move this to the middle one move. That would be 2, and that would be 3. So in general, it can be shown that it takes 2 times to the n minus 1 step to move such this to satisfy this rule. Now if we have 3, if we have 3 discs, it's going to be 2 to the 3rd power minus 1, so 7 move. Right, think about this. The objective is to move this, all 3 discs into here, but after all, it can be reduced to you move these 2 into the other. So in that case, you can move this there. Right? So of course we cannot move 2 discs at a time, only 1 disc at a time. So now, hypothetically, if you can move this 2 to the middle, and then you can move that to the 3rd. And now, if we want to move 2 to that, then that means we have move 1 to the intermediate step. Right, so now it will take 7 moves, right? So this is all. So first I will move here 1, 2, 3. Now if these 3 move, we move the n minus 1 onto the other one. Now 3, right? 4. Now the remaining task is move these 2 over there. Again, we already did that. Require 3 moves, right? So 4 moves total already. Now 5, 6, and 7. Right. So once again, in order to move 3 discs to the 3rd pack, we need to move 2 to the middle pack, and then after that we move the last one over there, and then move the other 2 over. Right. So bottom line, that's how the Taub-Harnoy problem works. Let me zoom back in. So the goal is to move all of this into that. Yeah. So the problem is, let's edge and denote the number of moves needed to move and this, and set up the recurrence. So we have that. We need to move. Okay. Just like this. If we want to move 3, that means we have to move 2 to the adjacent, to the other one, and then move 1 move to move the last disc, and then move the n minus 1 to there. So that's how the setup for the Taub-Harnoy problem. And with this we can say h of n equal to 2 to the n minus 1 plus 1, right? The n minus 1 is to move n minus 1 disc, to move n minus 1 disc to the other one, and then one move to move the last, and then move to n minus 1, move the n minus 1 back to the right one. So with that, we have this, and we solve for it, and it can be shown that it takes 2 to the n minus 1 step to do the tau Hanoi. Right. Next, counting big string. Find the recurrent relation and give the initial condition for the number of bits of string of length n, and give without 2 consecutive zeros. So the key here is without 2 consecutive zeros. So how many of such string? Now this is interesting. Now assume that n is greater than or equal to 3, because if we have 0, it could be 1 or 0. If we have length 1, length 2, it could be 1 1 1 0 0 1. Of course 0 0 doesn't count, and then so on. So we know those two, length 1, length 2. Now length 3, right here what we start, the bit string of length n that end with 1 without 2 consecutive 0 are the big string of n minus 1 with no 2 consecutive 0 with a 1 at the end. Hence they are a n minus 1 such big string. Right, so let's say we have up to a bunch of 0 1 up to the last one is 1. If that case, doesn't matter how many we have there, we add 0 to it at the end, then we have the same number of big string of the length n minus 1, right? So this is equal to a sub n minus 1. Next, the big string of length n with 0 without 2 consecutive 0 are big string of length n minus 2 with no consecutive. Right. Right. Now, the big string of length n with 0 without 2 consecutive are big string of n minus 2 with no 2 consecutive row with the 1 2 at the end. Right. So this is up to n minus 1. Right. Actually, this one doesn't matter if it's 1 or 0, could be 0 or 1. I'm just simple that by the box. So it doesn't matter if we start from, sorry, that was rather confusing. Right. So we have an n minus 1 string, and the last one, if it's 1 or 0, doesn't matter. If we put 1 at the end, we're not going to have 0 and 1. We have consecutive 0, right? It could be 0, it could be 1, doesn't matter. We just put 1 there, so that would be no consecutive zeros. So that's good. So we have n minus 1 of those. Now, if we have the one that only n minus 1, and it does whatever it ends with, we're going to have 2 more. If we're going to put 1 and 0, it's not going to have 2 consecutive 0, guaranteed for that. And this is n minus 2. And we just add those two together. Right, here's if the string ends with 1. Okay, now any big string of n minus 1 with no 2 consecutive 0, we just put 1 after it. There will be n minus 1 of those string, because it doesn't matter if the n minus 1 string, for example, if we have the string of 1 0 0 0, I'm sorry, cannot write that, 1 0 1, no 2 consecutive 0, right? Right, 1 1 0 1 0. Right, if it is the case, if we add 1 at the end, we're not going to have the 2 consecutive 0, right? Likewise, if we have the, if we're going to add 1 0 like this at the end, it's not going to be consecutive zeros, right? Now if there's n minus 1, this is n minus 2, this is n minus 1, so the string of n minus 2, we just add 1 0 to it, we have n minus 2 of those. And the string of n minus 1, we just add the 1 to it, we have a of n minus 1. So add those two, we have the same recurrent relation of the Fibonacci sequence, and some that behave just like Fibonacci sequence. So be 2, 3, 5, 8, 13, and so on. Originally there are 2, and then next one 3, so we have that sequence. Right, so with that, we finish section 8.1 in discrete math. As always, thank you for watching, and see you in another video in discrete math.